This next lecture is going to finish off chapter 4 from the book, looking at post-optimal analysis. Now, really, this is an extension of the sensitivity analysis. You remember when we did the sensitivity analysis, we were asking the question, how far can we change some of the parameters in our problem before we have to find a new solution to our problem? This is going one step further and saying, okay, now if we've changed our parameters so much that we need a new solution, how can we find a new solution? And this is looking at some ways to efficiently find a new solution. One option is always to take your problem and resolve it right from the start. But there's more efficient ways of finding the new solution. And that's what this is looking at. So this is a problem you've seen before a few times, the car manufacturer problem. We're going to use this as the basis, as the example for the ideas in this section. So if you recall, here was the problem sketched out so you can see it visually, what's happening. When you take this problem and put it into a tableau, there's two pivots that you do to find the solution. You get this final tableau. We are going to use this final tableau throughout sections of this lecture. So first off, here is the problem. This was our primal problem. This is our dual problem. Now, one thing that the book doesn't really highlight, but I want to point out, it's the idea of corresponding variables. If you have this idea in your head, it actually makes some of the ideas here flow a little bit easier, I think. So notice that when you do a primal and a dual, you have a correspondence between the variables. For instance, when you take your primal, your x1 column becomes your first constraint. Well, that first constraint, when you do the dual, there is a unique variable in there. It's your surplus variable. That corresponds to x1. So x1 corresponds to y5. The equation in your dual that you built from the x1 variables has a surplus variable, or a slack variable, depending on which way you're doing it, but it has that unique variable. There's a correspondence between them. Similarly, when you take a look at your first constraint, you use that first constraint as the coefficient for your y1. So that means this constraint has some kind of a correspondence to y1. What's the unique variable in here? x3. So x3 matches up with y1. So if you kind of keep this in the back of your head through some of these examples, it kind of helps to see, because there's this correspondence between your primal variables and your dual variables that exists kind of in the background. Okay, so when you start changing some of your parameters, there's a few things that can happen. Basically, four things that can happen. You have combinations between optimality and feasibility. So sometimes that your original solution remains optimal and feasible. Now let me explain what I mean by this. It doesn't necessarily mean that the exact point is going to stay the same. What it means is that things haven't shifted around enough that you have to redo a pivot in your tableau. So if you did 2 pivots to get to the solution, sometimes your new solution has the exact same 2 pivots. In which case you've done most of the work. Why can't we just make some adjustments to the final tableau to compensate? When you can, that's great. So when that happens and you don't have to do another pivot, we say that the solution is remaining optimal and feasible. And let's see what happens here. Essentially, no additional work, or very little additional work is required. So here's the example. Our original problem had the constraint 4x1 plus 6x2 is less than or equal to 720. Well, what if all of a sudden the hour availability for that machine drops and it becomes 4x1 plus 6x2 is less than or equal to 600? Well, graphically, you can see that this has the effect of moving that constraint down. But if you think about what the optimal line was on here, it is your optimal point is still going to be right there. It's still going to be the intersection of those two lines, which means that to get here, we did a pivot to move from one corner to a second corner, then to a third corner. You're going to be doing the exact same two pivots to get to this point. So that means that the current solution is remaining feasible and optimal when the pivots stay the same. Now, after you make the adjustment, think what happens in your original tableau. The only thing that's going to change in that original tableau is one of the numbers on the right-hand column. Every other number in that initial tableau stays the same. But now we're going to have two pivots. In each pivot, that number in the right-hand column could potentially affect every other number in the right-hand column. This is the tableau for your new problem after we've changed that constraint. Everything here is the exact same in the main body. Only the right-hand side may be changing. What I've given you here are the new numbers for the right-hand side. The question is, how did I get this? Without redoing all of the pivots, how can I get from my final tableau of my initial problem to the final tableau of this problem? And the answer lies in that inverse matrix that we talked about in the last lecture. So if you remember in the last lecture, we talked about how x1, x2, and x3, x3, x4, x5, and x6 in this particular problem would start out as having an identity matrix. Look at those columns here. This is what we termed the inverse matrix, but it's essentially the matrix that is going to allow us to transform from our initial tableau, the tableau in our initial problem, to the tableau in our new problem with the updated numbers. So here is our initial tableau. Our initial tableau with the new problem has this as the right-hand side. In the initial problem, that was a 720, now it's a 600. So that's changed. But now look at this. This is the matrix that we called the inverse matrix. It's columns x3, x4, x5, and x6 in our final tableau. Take that matrix, multiply it by the right-hand side, the new right-hand side, and what you get are the values that you just saw in the right-hand side of the new final tableau. This inverse matrix gives you a quick transformation without having to go through multiple pivots. It pulls together the impact of all of the pivots on that column. And in fact, it does it on every column. You could take any column from your original matrix, if you change it, multiply it by this identity matrix, or this inverse matrix, and you'll get the new column. So it gives you a shortcut to get from your initial tableau to your final tableau. And this is the final tableau. So you see the numbers that we have here on the right-hand side are exactly the same that I just calculated from a simple matrix multiplication. The only one I didn't comment on is this one, the value, which has changed as well. How do I get that? Well, keep in mind that I have my new values for x1, x2, x5, and x6. I can just plug them into my objective function and it gives me that value. Because that value is the value of the objective function. At any point, x1 is equal to 45, x2 is equal to 70, plug them into the initial objective function, and that'll give you 39,000. But note what's happened here. We've made this transformation. Think of it now in terms of the simplex. What does the simplex method say? Everything on the right-hand side is positive. All of the numbers in the Z column are positive. We're already at our optimal solution. We don't have to do anything else. One quick matrix multiplication, and we show that we have our new answer without having to do any more pivots. That was the easiest one, when you don't have to do anything else. But sometimes you change things around so much that you require some more pivots after you make the transformation. The idea of that inverse matrix is going to keep coming back over and over here. What if your current solution becomes infeasible? Here is a problem where it becomes infeasible. We had a constraint x1 greater than or equal to 20. Say that changes now to x1 greater than or equal to 40. Well, you can just kind of get an idea here now that the intersection of those two diagonal lines is no longer going to be our optimum value. That's in fact no longer a feasible point. So something has changed here, and we kind of get an idea that the problem itself is going to be different because our feasible region now looks very different. So what's going to happen here? Well, we're going to do the same exact thing. What happened? The difference from our original problem, we changed one of the right-hand columns, or one of the right-hand numbers on the constraints. Same exact thing. We're changing the right-hand side. How do we get that? The same exact way. Take your inverse matrix, multiply it by what your new right-hand side is, and get from what the new right-hand side would be from the initial problem, and you get the new right-hand side in your final tableau. So here's the inverse matrix. Here is the new initial tableau right-hand side. And see, the only difference here, we've gone back to the 720 from our original problem. Instead of having to make 20 cars, it forces you to make 40. So that gives you a new right-hand side. So the new right-hand side, oh, this was our initial tableau, gives you the new right-hand side. That's the only thing that's changed. In the new final tableau, these numbers are going to be the right-hand side. As we see here, here is our new right-hand side. Here is our new objective function value. But wait a minute, what do we have here now? We have made a change where the right-hand side suddenly has a negative number. That's not allowed. We are supposed to have positive numbers on the right-hand side in our final tableau. Fortunately, we just saw a method to solve this. When we have a number on the right-hand side that is negative, we can use the dual simplex method. So in this case, solve this with the dual simplex method using that -10 in the right-hand side. Find your pivot entry in that row using the rules we saw last time. Do another pivot. Sometimes you have to do another pivot or another pivot. But this tells you right away that you have made a drastic enough change that you now have to do another pivot because you've essentially changed the structure of your problem, of your solution. Okay. Another thing that can happen is that your current solution becomes non-optimal. So graphically, here's what's happening. This was our old objective. What's happening is our objective function is changing this time. This becomes our new objective function. And remember how it works? It's you kind of move it along parallel. So you can see as you slide this up, well, no longer the intersection of the points here is going to be your optimal. You can kind of see graphically that you are going to get a new optimal value that's right in here. Keeping in mind that this is your feasible region. Okay. So graphically, you can kind of see what's going to happen. And we're going to see here how to tell what's going on just in terms of the tableaus that you're seeing. So for this problem, we're taking our objective function 400x1 plus 300x2, and we're making a big change to it. It's becoming 300x1 plus 600x2. So this was types of cars. Car 2 becomes much more profitable. Car 1 becomes less profitable. So what's going to happen to our tableau? Now this gets a little more complex, but again, it's going to involve dealing with this matrix, which is the inverse matrix for the tableau, the final tableau. So what we have here, it was our original final tableau. What are basic variables? x6, x5, x2, and x1. You just read them from down here. 6, 5, 2, 1. 6, 5, 1, 2. Keeping them kind of in order. Okay? Because if you read down, you see x6 is the first column of your identity matrix, x5 is the second column of your identity matrix, and so on. Okay? So there is an order to them. So that as our basic variables. X3 and X4 are our non-basic variables. Remember the correspondences that I talked about? X3 kind of corresponds to Y1, X4 to Y2, Y3, Y4. X1 corresponded to Y5, and X2 corresponded to Y6. Okay, we're just going to keep that kind of in mind. It's not going to be a big thing, but it kind of helps to keep things clear sometimes. So now what's happened? Our original problem has changed our objective function. What we're asking now is when I make changes to my objective function, how does this change my overall tableau? And here are the ideas to keep in mind. So our new objective function is here. Maximize z equal 300x1 plus 600x2. Our basic variables were x6, 5, 1, and 2. The new values of those basic variables. Okay, now what I'm saying here is the new values in the initial tableau or the initial problem. In the initial tableau, x3, x4, x5, and x6 were the basic variables. So those were 0 originally. The coefficients, or they had 0 coefficients, because they don't appear in our objective function. The coefficients of our objective function for x1 and x2 are right there. So what we're looking at are the basic variables of the final tableau and saying, okay, in my original tableau, with my new objective function, what are the coefficients? And you'll note that those numbers appear on the top row of our initial tableau. But one of the things we saw in one of the previous classes is that you can use this inverse matrix to convert from your basic variables to your dual variables. Here's our basic variables in the order, in the same order that we had, times our inverse matrix. It gives us our dual variables. That's the values of our dual variables. From this, we can calculate our new top row. Y1, Y2, Y3, and Y4 corresponded to X4, 5, X3, 4, 5, and 6. That's our value for X3, X4, X5, and X6. Now, what about the other variables, X1 and X2? Well, in this case, X1 and X2 in our final tableau are non-basic variables, or sorry, are basic variables. That means they all automatically have a value of 0. That's what goes in the top row. They're basic variables, so zeros go in there. What about our non-basic variables? Well, those have to be calculated based on, go back to your dual problem and look at what line corresponds to X3. Well, X3 doesn't have one in there. It corresponds to the fact that Y1 is greater than or equal to 0. Y1 being greater than or equal to 0 means, well, how much slack or surplus do we have in there? What extra do we have in there? Well, Y1, we just calculated to be 112.5. So the extra that's in there is 112.5. That is the value of X3. And you see it matches with what we had up here. The problem in the book actually gives you one where there's a mixture of basic and non-basic variables here that go through that problem as well, keeping the same idea in mind. We also get the reduced cost of our second non-basic variable, which again happens to correspond to what we've calculated because it just happens to be in the set that we've calculated. The example that the book gives you has one that isn't in the set that you calculate, where you have to go and actually calculate the reduced cost from the equations. Now you've got the reduced costs and you put them in. So remember this top line, these are the reduced costs. So now you've entered your reduced costs, the numbers we calculated here, plus those are members of our basis, so they're 0. Sometimes you have to calculate some additional ones, such as with the problem in the book, but now we have our reduced costs. So you've now changed the final tableau into your updated final tableau. And now you can take a look at this and see what you have. Well, now you have a positive number up here. The rules for simplex method say that when you have a positive number there, you have another pivot to do. Go ahead and do the pivot. It means that you have bypassed having to do all the pivots up to this point, and you kind of pick up your problem at this point and make it easier. The other thing that can happen is a combination of the problems that we just saw, where you end up with a non-optimal and infeasible. So what you end up with is positive numbers on your objective function. You end up with negative numbers on your right-hand side, some combination of it, or when you start doing pivots, it flips back and forth. When that happens, you essentially just have to do the dual simplex and the primal simplex back and forth as required. All right, so this chapter was kind of heavy. It was looking at a lot of ideas, but the main idea here is to is using what we saw last time, using this idea of the matrix that's embedded in your tableau to skip from a new initial tableau to a final tableau without having to redo all of your calculations. How to transform your final tableau into a new final tableau when you've changed your constraints or when you've changed your objective function a little bit. It's a big time saver, especially since some of these problems can be quite intensive to calculate, but it's an important concept to kind of understand and go through some of the problems in the book.